A neutrino is an electrically neutral, weakly interacting elementary subatomic particle with half-integer spin. The neutrino is denoted by the Greek letter I1/2. All evidence suggests that neutrinos have mass, but the upper bounds established for their mass are tiny even by the standards of subatomic particles. Neutrinos do not carry electric charge, which means that they are not affected by the electromagnetic forces that act on charged particles such as electrons and protons. Neutrinos are affected only by the weak subatomic force, of much shorter range than electromagnetism, and gravity, which is relatively weak on the subatomic scale. Therefore a typical neutrino passes through normal matter unimpeded. Neutrinos are created as a result of certain types of radioactive decay, or nuclear reactions such as those that take place in the Sun, in nuclear reactors, or when cosmic rays hit atoms. There are three types, or flavors, of neutrinos: electron neutrinos, muon neutrinos and tau neutrinos. Each type is associated with an antiparticle, called a non-tau neutrino, which also has neutral electric charge and half-integer spin. Whether or not the neutrino and its corresponding non-tau neutrino are identical particles has not yet been resolved, even though the non-tau neutrino has an opposite chirality to the neutrino. Most neutrinos passing through the Earth emanate from the Sun. About 65 billion solar neutrinos per second pass through every square centimeter perpendicular to the direction of the Sun in the region of the Earth. History: Pauli's proposal. The neutrino was postulated first by Wolfgang Pauli in 1930 to explain how beta decay could conserve energy, momentum, and angular momentum. In contrast to Niels Bohr, who proposed a statistical version of the conservation laws to explain the event, Pauli hypothesized an undetected particle that he called a neutron, in keeping with convention employed for naming both the proton and the electron, which in 1930 were known to be respective products for alpha and beta decay. NOAP++ A plus I1/2, E. James Chadwick discovered a much more massive nuclear particle in 1932 and also named it a neutron, leaving two kinds of particles with the same name. Enrico Fermi, who developed the theory of beta decay, coined the term neutrino in 1933 as a way to resolve the confusion. Fermi's paper, written in 1934, unified Pauli's neutrino with Paul Dirac's positron and Werner Heisenberg's neutron-proton model and gave a solid theoretical basis for future experimental work. However, the journal Nature rejected Fermi's paper, saying that the theory was too remote from reality. He submitted the paper to an Italian journal, which accepted it, but the general lack of interest in his theory at that early date caused him to switch to experimental physics. Direct detection. In 1942, Wang Gangkang first proposed the use of beta capture to experimentally detect neutrinos. In the 20th July 1956 issue of Science, Clyde Cowan, Frederick Rains, F. B. Harrison, H. W. Cruz, and A. D. McGuire published confirmation that they had detected the neutrino, a result that was rewarded almost 40 years later with the 1995 Nobel Prize. In this experiment, now known as the Cowan-Rains neutrino experiment, non-tau neutrinos created in a nuclear reactor by beta decay reacted with protons producing neutrons and positrons, I1/2, E plus P plus A and O plus E plus. The positron quickly finds an electron, and they annihilate each other. The two resulting gamma rays are detectable. The neutron can be detected by its capture on an appropriate nucleus, releasing a gamma ray. The coincidence of both events, a positron annihilation and neutron capture, gives a unique signature of a non-tau neutrino interaction. Neutrino flavor. In 1962, Leon M. Lederman, Melvin Schwartz and Jack Steinberger showed that more than one type of neutrino exists by first detecting interactions of the muon neutrino, which earned them the 1988 Nobel Prize in Physics. When the third type of lepton, the tau, was discovered in 1975 at the Stanford Linear Accelerator Center, it too was expected to have an associated neutrino. First evidence for this third neutrino type came from the observation of missing energy and momentum in tau decays analogous to the beta decay, leading to the discovery of the neutrino. The first detection of tau neutrino interactions was announced in summer of 2000 by the Donut collaboration at Fermilab. Its existence had already been inferred by both theoretical consistency and experimental data from the Large Electron-Positron Collider. Solar neutrino problem. Starting in the late 1960s, several experiments found that the number of electron neutrinos arriving from the Sun was between 1/3 and 1/2 the number predicted by the standard solar model. This discrepancy, which became known as the solar neutrino problem, remained unresolved for some 30 years. It was resolved by discovery of neutrino oscillation and mass oscillation. A practical method for investigating neutrino oscillations was first suggested by Bruno Pontecorvo in 1957 using an analogy with Kohn oscillations. Over the subsequent 10 years he developed the mathematical formalism and the modern formulation of vacuum oscillations. In 1985 Stanislav Mikhayev and Alexei Smirnov noted that flavor oscillations can be modified when neutrinos propagate through matter. This so-called Mikhayev-Smirnov-Wolfenstein effect is important to understand because many neutrinos emitted by fusion in the Sun pass through the dense matter in the solar core on their way to detectors on Earth. Starting in 1998, experiments began to show that solar and atmospheric neutrinos change flavors. This resolved the solar neutrino problem. The electron neutrinos produced in the Sun had partly changed into other flavors which the experiments could not detect. Although individual experiments, such as the set of solar neutrino experiments, are consistent with non-oscillatory mechanisms of neutrino flavor conversion, taken all together, neutrino experiments imply the existence of neutrino oscillations. Especially relevant in this context are the reactor experiment KAM-LAND and the accelerator experiments such as MINOS. The KAM-LAND experiment has indeed identified oscillations as the neutrino flavor conversion mechanism involved in the solar electron neutrinos. Similarly, MINOS confirms the oscillation of atmospheric neutrinos and gives a better determination of the mass-squared splitting. Supernova neutrinos. Raymond Davis, J.R. and Masatoshi Koshiba were jointly awarded the 2002 Nobel Prize in Physics. Davis for his pioneer work on cosmic neutrinos and Koshiba for the first real-time observation of supernova neutrinos. The detection of solar neutrinos, and of neutrinos of the SN 1987A supernova in 1987 marked the beginning of neutrino astronomy. Properties and reactions. The neutrino has half-integer spin and is therefore a fermion. Neutrinos interact primarily through the weak force. The discovery of neutrino flavor oscillations implies that neutrinos have mass. The existence of a neutrino mass strongly suggests the existence of a tiny neutrino magnetic moment of the order of 10 in 19 AI1/4b, allowing the possibility that neutrinos may interact electromagnetically as well. An experiment done by C.S. Wu at Columbia University showed that neutrinos always have left-handed chirality. It is very hard to uniquely identify neutrino interactions among the natural background of radioactivity. For this reason, in early experiments a special reaction channel was chosen to facilitate the identification, the interaction of an entire neutrino with one of the hydrogen nuclei in the water molecules. A hydrogen nucleus is a single proton. So simultaneous nuclear interactions, which would occur within a heavier nucleus, don't need to be considered for the detection experiment. Within a cubic meter of water placed right outside a nuclear reactor, only relatively few such interactions can be recorded, but the setup is now used for measuring the reactor's plutonium production rate. Mikhayev-Smirnov-Wolfenstein effect. Neutrinos traveling through matter, in general, undergo a process analogous to light traveling through a transparent material. This process is not directly observable because it does not produce ionizing radiation, but gives rise to the MSW effect. Only a small fraction of the neutrino's energy is transferred to the material. Nuclear reactions. Neutrinos can interact with a nucleus, changing it to another nucleus. This process is used in radiochemical neutrino detectors. In this case, the energy levels and spin states within the target nucleus have to be taken into account to estimate the probability for an interaction. In general, the interaction probability increases with the number of neutrons and protons within a nucleus. Induced fission, very much like neutrons do in nuclear reactors, neutrinos can induce fission reactions within heavy nuclei. So far, this reaction has not been measured in a laboratory, but is predicted to happen within stars and supernovae. The process affects the abundance of isotopes seen in the universe. Neutrino fission of deuterium nuclei has been observed in the Sudbury Neutrino Observatory, which uses a heavy water detector. Types: there are three known types of neutrinos: electron neutrino I1/2, E, muon neutrino I1/2, I1/4 and tau neutrino I1/2, I, named after their partner leptons in the Standard Model. The current best measurement of the number of neutrino types comes from observing the decay of the Z boson. This particle can decay into any light neutrino and its entire neutrino, and the more types of light neutrinos available, the shorter the lifetime of the Z boson. Measurements of the Z lifetime have shown that the number of light neutrino types is 3. The correspondence between the 6 quarks in the Standard Model and the 6 leptons, among them the 3 neutrinos, suggests to physicists' intuition that there should be exactly 3 types of neutrino. However, actual proof that there are only 3 kinds of neutrinos remains an elusive goal of particle physics. The possibility of sterile neutrinos are relatively light neutrinos which do not participate in the weak interaction but which could be created through flavor oscillation is unaffected by these Z boson-based measurements, and the existence of such particles is in fact hinted by experimental data from the LSND experiment. However, the currently running mini-Booney experiment suggested, until recently, that sterile neutrinos are not required to explain the experimental data, although the latest research into this area is ongoing and anomalies in the mini-Booney data may allow for exotic neutrino types, including sterile neutrinos. A recent reanalysis of reference electron spectra data from the Institut Laue-Langevin has also hinted at a 4th, sterile neutrino. Recently analyzed data from the Wilkinson microwave anisotropy probe of the cosmic background radiation is compatible with either 3 or 4 types of neutrinos. It is hoped that the addition of 2 more years of data from the probe will resolve this uncertainty. Entire neutrinos. Entire neutrinos are the antiparticles of neutrinos, which are neutral particles produced in nuclear beta decay. These are emitted during beta particle emissions, when a neutron turns into a proton. They have a spin of a 1/2, and are part of the lepton family of particles. The entire neutrinos observed so far all have right-handed helicity, while the neutrinos are left-handed. Entire neutrinos, like neutrinos, interact with other matter only through the gravitational and weak forces, making them very difficult to detect experimentally. Neutrino oscillation experiments indicate that entire neutrinos have mass, but beta decay experiments constrain that mass to be very small. A neutrino-entire neutrino interaction has been suggested in attempts to form a composite photon with the neutrino theory of light. Because entire neutrinos and neutrinos are neutral particles, it is possible that they are actually the same particle. Particles which have this property are known as Majorana particles. If neutrinos are indeed Majorana particles, then the neutrino-less double beta decay, as well as a range of other lepton number violating phenomena, are allowed. Several experiments have been proposed to search for this process. Researchers around the world have begun to investigate the possibility of using entire neutrinos for reactor monitoring in the context of preventing the proliferation of nuclear weapons. Entire neutrinos were first detected as a result of their interaction with protons in a large tank of water. This was installed next to a nuclear reactor as a controllable source of the entire neutrinos. Only entire neutrinos, and not neutrinos, take part the Glasgow resonance. Flavor oscillations. Neutrinos are most often created or detected with a well-defined flavor. However, in a phenomenon known as neutrino flavor oscillation, neutrinos are able to oscillate among the 3 available flavors while they propagate through space. Specifically, this occurs because the neutrino flavor eigenstates are not the same as the neutrino mass eigenstates. This allows for a neutrino that was produced as an electron neutrino at a given location to have a calculable probability to be detected as either a muon or tau neutrino after it has traveled to another location. This quantum mechanical effect was first hinted by the discrepancy between the number of electron neutrinos detected from the Sun's core failing to match the expected numbers, dubbed as the solar neutrino problem. In the Standard Model, the existence of flavor oscillations implies non-zero differences between the neutrino masses, because the amount of mixing between neutrino flavors at a given time depends on the differences between their squared masses. There are other possibilities in which neutrino can oscillate even if they are massless. If Lorentz invariance is not in exact symmetry, neutrinos can experience Lorentz-violating oscillations. It is possible that the neutrino and tau neutrino are in fact the same particle, a hypothesis first proposed by the Italian physicist Ettore Majorana. The neutrino could transform into a tau neutrino by flipping the orientation of its spin state. This change in spin would require the neutrino and tau neutrino to have non-zero mass, and therefore travel slower than light, because such a spin flip, caused only by a change in point of view, can take place only if inertial frames of reference exist that move faster than the particle. Such a particle has a spin of one orientation when seen from a frame which moves slower than the particle, but the opposite spin when observed from a frame that moves faster than the particle. On July 19, 2013, the results from the T2K experiment presented at the European Physical Society Conference on High-Energy Physics in Stockholm, Sweden, confirmed the neutrino oscillation theory. Speed. Before neutrinos were found to oscillate, they were generally assumed to be massless, propagating at the speed of light. According to the theory of special relativity, the question of neutrino velocity is closely related to their mass. If neutrinos are massless, they must travel at the speed of light. However, if they have mass, they cannot reach the speed of light. Also, some Lorentz-violating variants of quantum gravity might allow faster-than-light neutrinos. A comprehensive framework for Lorentz violations is the Standard Model extension. In the early 1980s, first measurements of neutrino speed were done using pulsed pion beams. The pions decayed producing neutrinos, and the neutrino interactions observed within a time window in a detector at a distance were consistent with the speed of light. This measurement was repeated in 2007 using the MINOS detectors, which found the speed of 3 GeV neutrinos to be 1.000051, 29, AC at 68% confidence level, and at 99% confidence level a range between 0.999976 AC and 1.000126 AC. The central value is higher than the speed of light and is consistent with superluminal velocity. However, the uncertainty is great enough that the result also does not rule out speeds less than or equal to light at this high confidence level. This measurement set an upper bound on the mass of the muon neutrino of 50 MeV at 99% confidence. After the detectors for the project were upgraded in 2012, MINOS corrected their initial result and found agreement with the speed of light, with limits for the difference in the arrival time of light and neutrinos of nanoseconds. Further measurements are going to be conducted. The same observation was made, on a somewhat larger scale, with supernova 1987. 8 MeV tau neutrinos from the supernova were detected within a time window that was consistent with the speed of light for the neutrinos. So far, the question of neutrino masses cannot be decided based on measurements of the neutrino speed. In September 2011, the Opera collaboration released calculations showing velocities of 17 GeV and 28 GeV neutrinos exceeding the speed of light in their experiments. In November 2011, Opera repeated its experiment with changes so that the speed could be determined individually for each detected neutrino. The results showed the same faster-than-light speed. However, in February 2012 reports came out that the results may have been caused by a loose fiber optic cable attached to one of the atomic clocks which measured the departure and arrival times of the neutrinos. An independent recreation of the experiment in the same laboratory by Icarus found no discernible difference between the speed of a neutrino and the speed of light. In June 2012, CERN announced that new measurements conducted by 4-gram SASO experiments found agreement between the speed of light and the speed of neutrinos, finally refuting the initial OPERA result. Mass. The standard model of particle physics assumed that neutrinos are massless. However, the experimentally established phenomenon of neutrino oscillation, which mixes neutrino flavor states with neutrino mass states, requires neutrinos to have non-zero masses. Massive neutrinos were originally conceived by Bruno Pontecorvo in the 1950s. Enhancing the basic framework to accommodate their mass is straightforward by adding a right-handed Lagrangian. This can be done in two ways. If, like other fundamental standard model particles, mass is generated by the Dirac mechanism, then the framework would require a SU singlet. This particle would have no other standard model interactions, so is called a sterile neutrino. Or, mass can be generated by the Majorana mechanism, which would require the neutrino and antineutrino to be the same particle. The strongest upper limit on the masses of neutrinos comes from cosmology. The Big Bang model predicts that there is a fixed ratio between the number of neutrinos and the number of photons in the cosmic microwave background. If the total energy of all three types of neutrinos exceeded an average of 50 eV per neutrino, there would be so much mass in the universe that it would collapse. This limit can be circumvented by assuming that the neutrino is unstable. However, there are limits within the standard model that make this difficult. A much more stringent constraint comes from a careful analysis of cosmological data, such as the cosmic microwave background radiation, galaxy surveys, and the Lyman alpha forest. These indicate that the summed masses of the three neutrinos must be less than 0.3 eV. In 1998, research results at the Super-Kamiokande neutrino detector determined that neutrinos can oscillate from one flavor to another, which requires that they must have a non-zero mass. While this shows that neutrinos have mass, the absolute neutrino mass scale is still not known. This is because neutrino oscillations are sensitive only to the difference in the squares of the masses. The best estimate of the difference in the squares of the masses of mass eigenstates 1 and 2 was published by K.A.M. Land in 2005, IM2, 21 equals a 0.000079 eV2. In 2006, the MINOS experiment measured oscillations from an intense muon neutrino beam, determining the difference in the squares of the masses between neutrino mass eigenstates 2 and 3. The initial results indicate IM2, 32 equals a 0.0027 eV2, consistent with previous results from Super-Kamiokande. Since IM2, 32 is the difference of two squared masses, at least one of them has to have a value which is at least the square root of this value. Thus, there exists at least one neutrino mass eigenstate with a mass of at least 0.04 eV. In 2009, lensing data of a galaxy cluster were analyzed to predict a neutrino mass of about 1.5 eV. All neutrino masses are then nearly equal, with neutrino oscillations of order μv. They lie below the Mainz-Troitsky upper bound of 2.2 eV for the electron antineutrino. The latter will be tested in 2015 in the Katrin experiment, that searches for a mass between 0.2 eV and 2 eV. A number of efforts are underway to directly determine the absolute neutrino mass scale in laboratory experiments. The methods applied involve nuclear beta decay or neutrino-less double beta decay. On May 31, 2010, OPERA researchers observed the first tau neutrino candidate event in a muon neutrino beam, the first time a transformation in neutrinos had been observed, giving evidence that they have mass. In July 2010, a 3D MEGA-ZDR7 galaxy survey reported that they had measured a limit of the combined mass of the three neutrino varieties to be less than 0.28 eV. A tighter upper bound yet for this sum of masses, 0.23 eV, was reported in March 2013 by the Planck collaboration, whereas a February 2014 result estimates the sum as 0.320 plus or minus 0.081 eV based on discrepancies between the cosmological consequences implied by Planck's detailed measurements of the cosmic microwave background and predictions arising from observing other phenomena. combined with the assumption that neutrinos are responsible for the observed weaker gravitational lensing than would be expected from massless neutrinos. If the neutrino is a Majorana particle, the mass can be calculated by finding the half-life of neutrino-less double beta decay of certain nuclei. The lowest upper limit, on the Majorana mass of the neutrino, has been set by EXO 200-140 Euro 380 MeV, size. Standard model neutrinos are fundamental point-like particles, so they have zero volume. An effective size can be defined using their electroweak radius. The average electroweak characteristic size is I/2I copyright equals Na, 10 of 33 cm 2, where N equals 3.2 for electron neutrino, N equals 1.7 for muon neutrino and 1.0 for tau neutrino. It depends on no other properties than mass. However, this is best understood as being relevant only to probability of scattering. Since the neutrino does not interact electromagnetically, and is defined quantum mechanically by a wave function instead of a single point in space, it does not have a size in the same sense as everyday objects. Furthermore, processes that produce neutrinos impart such high energies to them that they travel at almost the speed of light. Nevertheless, neutrinos are fermions, and thus obey the Pauli exclusion principle, that is, in principle they are solid objects that cannot be packed into arbitrary densities. Chirality. Experimental results show that all produced and observed neutrinos have left-handed helicities, and all entire neutrinos have right-handed helicities, within the margin of error. In the massless limit, it means that only one of two possible chiralities is observed for either particle. These are the only chiralities included in the standard model of particle interactions. It is possible that their counterparts simply do not exist. If they do, their properties are substantially different from observable neutrinos and antineutrinos. It is theorized that they are either very heavy, do not participate in weak interaction, or both. The existence of non-zero neutrino masses somewhat complicates the situation. Neutrinos are produced in weak interactions as chirality eigenstates. However, chirality of a massive particle is not a constant of motion. Helicity is, but the chirality operator does not share eigenstates with the helicity operator. Free neutrinos propagate as mixtures of left and right-handed helicity states, with mixing amplitudes on the order of μ½ This does not significantly affect the experiments, because neutrinos involved are nearly always ultra-relativistic, and thus mixing amplitudes are vanishingly small. For example, most solar neutrinos have energies on the order of 100 eV 1 MeV, so the fraction of neutrinos with wrong helicity among them cannot exceed 10^10. Sources: artificial, reactor neutrinos. Nuclear reactors are the major source of human-generated neutrinos. Entire neutrinos are made in the beta decay of neutron-rich daughter fragments in the fission process. Generally, the four main isotopes contributing to the entire neutrino flux are 235U, 238U, 239Pu and 241Pu. The average nuclear fission releases about 200 MeV of energy, of which roughly 4.5% is radiated away as entire neutrinos. For a typical nuclear reactor with a thermal power of 4000 EMW, meaning that the core produces this much heat, and an electrical power generation of 1300 MW, the total power production from fissioning atoms is actually 4185 EMW, of which 185 EMW is radiated away as entire neutrino radiation and never appears in the engineering. This is to say, 185 EMW of fission energy is lost from this reactor and does not appear as heat available to run turbines, since the entire neutrinos penetrate all building materials essentially without any trace, and disappear. The entire neutrino energy spectrum depends on the degree to which the fuel is burned, but in general, the detectable entire neutrinos from fission have a peak energy between about 3.5 and 4 MeV, with a maximum energy of about 10 MeV. There is no established experimental method to measure the flux of low-energy entire neutrinos. Only entire neutrinos with an energy above threshold of 1.8 MeV can be uniquely identified. An estimated 3% of all entire neutrinos from a nuclear reactor carry an energy above this threshold. Thus, an average nuclear power plant may generate over 10-20 neutrinos per second above this threshold, but also a much larger number below the energy threshold, which cannot be seen with present detector technology. Accelerator neutrinos. Some particle accelerators have been used to make neutrino beams. The technique is to smash protons into a fixed target, producing charged pions or quarks. These unstable particles are then magnetically focused into a long tunnel where they decay while in flight. Because of the relativistic boost of the decaying particle, the neutrinos are produced as a beam rather than isotropically. Efforts to construct an accelerator facility where neutrinos are produced through muon decays are ongoing. Such a setup is generally known as a neutrino factory. Nuclear bombs. Nuclear bombs also produce very large quantities of neutrinos. Fred Raines and Clyde Cowan considered the detection of neutrinos from a bomb prior to their search for reactor neutrinos. A fission reactor was recommended as a better alternative by Los Alamos Physics Division leader J.M.B. Kellogg. Fission bombs produce neutrinos, and fusion bombs produce both neutrinos and neutrinos. Geologic. Neutrinos are part of the natural background radiation. In particular, the decay chains of 238U and 232nd isotopes, as well as 40K, include beta decays which emit neutrinos. These so-called G-neutrinos can provide valuable information on the Earth's interior. A first indication for G-neutrinos was found by the KAM Land experiment in 2005. KAM Land's main background in the G-neutrino measurement are the neutrinos coming from reactors. Several future experiments aim at improving the G-neutrino measurement, and these will necessarily have to be far away from reactors. Atmospheric neutrinos result from the interaction of cosmic rays with atomic nuclei in the Earth's atmosphere, creating showers of particles, many of which are unstable and produce neutrinos when they decay. A collaboration of particle physicists from Tata Institute of Fundamental Research, Osaka City University and Durham University recorded the first cosmic ray neutrino interaction in an underground laboratory in Kola gold fields in India in 1965. Solar neutrinos originate from the nuclear fusion powering the Sun and other stars. The details of the operation of the Sun are explained by the standard solar model. In short, when 4 protons fuse to become one helium nucleus, 2 of them have to convert into neutrons, and each such conversion releases 1 electron neutrino. The Sun sends enormous numbers of neutrinos in all directions. Each second, about 65 billion solar neutrinos pass through every square centimeter on the part of the Earth that faces the Sun. Since neutrinos are insignificantly absorbed by the mass of the Earth, the surface area on the side of the Earth opposite the Sun receives about the same number of neutrinos as the side facing the Sun, supernovae. In 1966, Colgate and White calculated that neutrinos carry away most of the gravitational energy released by the collapse of massive stars, events now categorized as Type Ia and Ic and Type II supernovae. When such stars collapse, matter densities at the core becomes so high that the degeneracy of electrons is not enough to prevent protons and electrons from combining to form a neutron and an electron neutrino. A second and more important neutrino source is the thermal energy of the newly formed neutron core, which is dissipated via the formation of neutrino or neutrino pairs of all flavors. Colgate and White's theory of supernova neutrino production was confirmed in 1987, when neutrinos from supernova 1987A were detected. The water-based detectors CAMACAN 2 and IMB detected 11 and 8 neutrinos of thermal origin, respectively, while the scintillator-based BACSAN detector found 5 neutrinos of either thermal or electron capture origin, in a burst lasting less than 13 seconds. The neutrino signal from the supernova arrived at Earth several hours before the arrival of the first electromagnetic radiation, as expected from the evident fact that the latter emerges along with the shock wave. The exceptionally feeble interaction with normal matter allowed the neutrinos to pass through the churning mass of the exploding star, while the electromagnetic photons were slowed. Because neutrinos interact so little with matter, it is thought that a supernova's neutrino emissions carry information about the innermost regions of the explosion. Much of the visible light comes from the decay of radioactive elements produced by the supernova shock wave, and even light from the explosion itself is scattered by dense and turbulent gases. Neutrinos, on the other hand, pass through these gases, providing information about the supernova core. Furthermore, the neutrino burst is expected to reach Earth before any electromagnetic waves, including visible light, gamma rays or radio waves. The exact time delay depends on the velocity of the shock wave and on the thickness of the outer layer of the star. For a Type II supernova, astronomers expect the neutrino flood to be released seconds after the stellar core collapse, while the first electromagnetic signal may emerge hours later. The SNEWS project uses a network of neutrino detectors to monitor the sky for candidate supernova events. The neutrino signal will provide a useful advance warning of a star exploding in the Milky Way. Supernova remnants. The energy of supernova neutrinos ranges from a few to several tens of MeV. However, the sites where cosmic rays are accelerated are expected to produce neutrinos that are at least 1 million times more energetic, produced from turbulent gaseous environments left over by supernova explosions, the supernova remnants. The origin of the cosmic rays was attributed to supernovas by Walter Baade and Fritz Zwicky. This hypothesis was refined by Vitaly Alginsberg and Sergei Isaravatsky, who attributed the origin to supernova remnants, and supported their claim by the crucial remark, that the cosmic ray losses of the Milky Way is compensated, if the efficiency of acceleration in supernova remnants is about 10%. Ginsberg and Isaravatsky's hypothesis is supported by the specific mechanism of shock wave acceleration happening in supernova remnants, which is consistent with the original theoretical picture drawn by Enrico Fermi, and is receiving support from observational data. The very high-energy neutrinos are still to be seen, but this branch of neutrino astronomy is just in its infancy. The main existing or forthcoming experiments that aim at observing very high-energy neutrinos from our galaxy are Baikal, Amanda, IceCube, Antares, NEMO and Nestor. Related information is provided by very high-energy gamma-ray observatories, such as Veritas, HESS and MAGIC. Indeed, the collisions of cosmic rays are supposed to produce charged pions, whose decay give the neutrinos, and also neutral pions, whose decay give gamma rays. The environment of a supernova remnant is transparent to both types of radiation. Still higher energy neutrinos, resulting from the interactions of extragalactic cosmic rays, could be observed with the Pierre Auger Observatory or with the dedicated experiment named ANITA, Big Bang. It is thought that, just like the cosmic microwave background radiation left over from the Big Bang, there is a background of low-energy neutrinos in our universe. In the 1980s it was proposed that these may be the explanation for the dark matter thought to exist in the universe. Neutrinos have one important advantage over most other dark matter candidates: we know they exist. However, they also have serious problems. From particle experiments, it is known that neutrinos are very light. This means that they easily move at speeds close to the speed of light. Thus, dark matter made from neutrinos is termed hot dark matter. The problem is that being fast-moving, the neutrinos would tend to have spread out evenly in the universe before cosmological expansion made them cold enough to congregate in clumps. This would cause the part of dark matter made of neutrinos to be smeared out and unable to cause the large galactic structures that we see. Further, these same galaxies and groups of galaxies appear to be surrounded by dark matter that is not fast enough to escape from those galaxies. Presumably this matter provided the gravitational nucleus for formation. This implies that neutrinos make up only a small part of the total amount of dark matter. From cosmological arguments, relic background neutrinos are estimated to have density of 56 of each type per cubic centimeter and temperature 1.9 K if they are massless, much colder if their mass exceeds 0.001 eV. Although their density is quite high, they have not yet been observed in the laboratory, as their energy is below thresholds of most detection methods, and due to extremely low neutrino interaction cross-sections at sub-eV energies. In contrast, boron-8 solar neutrinos are Euro which are emitted with a higher energy have been detected definitively despite having a space density that is lower than that of relic neutrinos by some 6 orders of magnitude. Detection. Neutrinos cannot be detected directly, because they do not ionize the materials they are passing through. A unique reaction to identify neutrinos, sometimes referred to as inverse beta decay, as applied by Raines and Cowan, requires a very large detector in order to detect a significant number of neutrinos. All detection methods require the neutrinos to carry a minimum threshold energy. So far, there is no detection method for low-energy neutrinos, in the sense that potential neutrino interactions cannot be uniquely distinguished from other causes. Neutrino detectors are often built underground in order to isolate the detector from cosmic rays and other background radiation. Neutrinos were first detected in the 1950s near a nuclear reactor. Raines and Cowan used 2 targets containing a solution of cadmium chloride in water. 2 scintillation detectors were placed next to the cadmium targets. Neutrinos with an energy above the threshold of 1.8 MeV caused charged current interactions with the protons in the water, producing positrons and neutrons. This is very much like I² plus decay, where energy is used to convert a proton into a neutron, a positron and an electron. Neutrino, I½ E, is emitted, from known I² plus decay, energy plus PAN plus E plus I½ E. In the Cowan and Raines experiment, instead of an outgoing neutrino, you have an incoming neutrino, I½ E, from a nuclear reactor, energy plus P plus I½ EAN plus E plus. The resulting positron annihilation with electrons in the detector material created photons with an energy of about 0.5 MeV. Pairs of photons in coincidence could be detected by the 2 scintillation detectors above and below the target. The neutrons were captured by cadmium nuclei, resulting in gamma rays of about 8 MeV that were detected a few microseconds after the photons from a positron annihilation event. Since then, various detection methods have been used. Supercamicand is a large volume of water surrounded by photomultiplier tubes that watch for the Cherenkov radiation emitted when an incoming neutrino creates an electron or muon in the water. The Sudbury Neutrino Observatory is similar, but uses heavy water as the detecting medium, which uses the same effects, but also allows the additional reaction any flavor neutrino photodissociation of deuterium, resulting in a free neutron which is then detected from gamma radiation after chlorine capture. Other detectors have consisted of large volumes of chlorine or gallium which are periodically checked for excesses of argon or germanium, respectively, which are created by electron neutrinos interacting with the original substance. MINOS uses a solid plastic scintillator coupled to photomultiplier tubes, while BalkSino uses a liquid pseudocumen scintillator also watched by photomultiplier tubes, and the proposed NOI-1/2A detector will use liquid scintillator watched by avalanche photodiodes. The Ice Cube Neutrino Observatory uses 1 km3 of the Antarctic ice sheet near the South Pole with photomultiplier tubes distributed throughout the volume. Motivation for scientific interest. Neutrinos' low mass and neutral charge mean they interact exceedingly weakly with other particles and fields. This feature of weak interaction interests scientists because it means neutrinos can be used to probe environments that other radiation cannot penetrate. Using neutrinos as a probe was first proposed in the mid-20th century as a way to detect conditions at the core of the Sun. The solar core cannot be imaged directly because electromagnetic radiation is diffused by the great amount and density of matter surrounding the core. On the other hand, neutrinos pass through the Sun with few interactions. Whereas photons emitted from the solar core may require 40,000 years to diffuse to the outer layers of the Sun, neutrinos generated in stellar fusion reactions at the core cross this distance practically unimpeded at nearly the speed of light. Neutrinos are also useful for probing astrophysical sources beyond our solar system because they are the only known particles that are not significantly attenuated by their travel through the interstellar medium. Optical photons can be obscured or diffused by dust, gas, and background radiation. High-energy cosmic rays, in the form of swift protons and atomic nuclei, are unable to travel more than about 100 megapascals due to the Grassner-Zatsepina-Kuzmin limit. Neutrinos, in contrast, can travel even greater distances barely attenuated. The galactic core of the Milky Way is fully obscured by dense gas and numerous bright objects. Neutrinos produced in the galactic core might be measurable by Earth-based neutrino telescopes. Another important use of the neutrino is in the observation of supernovae, the explosions that end the lives of highly massive stars. The core collapse phase of a supernova is an extremely dense and energetic event. It is so dense that no known particles are able to escape the advancing core front except for neutrinos. Consequently, supernovae are known to release approximately 99% of their radiant energy in a short burst of neutrinos. These neutrinos are a very useful probe for core collapse studies. The rest mass of the neutrino is an important test of cosmological and astrophysical theories. The neutrino's significance in probing cosmological phenomena is as great as any other method, and is thus a major focus of study in astrophysical communities. The study of neutrinos is important in particle physics because neutrinos typically have the lowest mass, and hence are examples of the lowest energy particles theorized in extensions of the Standard Model of particle physics. In November 2012, American scientists used a particle accelerator to send a coherent neutrino message through 780 feet of rock. This marks the first use of neutrinos for communication, and future research may permit binary neutrino messages to be sent immense distances through even the densest materials, such as the Earth's core. See also: List of neutrino experiments, notes. References. Bibliography. External links. What's a neutrino? Dave Casper, Neutrino Unbound, Online Review and e-archive on Neutrino Physics and Astrophysics, Nova, The Ghost Particle, documentary on U.S. public television from WGBH, Measuring the Density of the Earth's Core with Neutrinos, Universe Submerged in a Sea of Chilled Neutrinos, New Scientist, March 5, 2008, What's a neutrino? Search for neutrino Illis double beta decay with enriched 76 GeV in Gran Sasso 1990 Euro 2003, neutrino caught in the act of changing from muon type to tau type, CERN press release, cosmic weight gain, a wispy particle bulks up by George Johnson, neutrino ghost particle sized up by astronomers BBC News June 22, 2010, Pillar of Physics challenged, Merrifield, Michael. Copeland, ed. Bowley, Roger. Neutrinos. 60 Symbols. Brady Heron for the University of Nottingham. The Neutrino with Dr. Clyde L. Cowan.